All right. So that should end up working on the live stream now. I'll make sure that it works here in a second. Anyway, error handling. What did we do? Well, programs always have the potential for errors, right? There are some errors that you cannot possibly recover from. External errors like somebody kicking out the power cord or something, right? There's no way that you can program software to reach out of the screen and replug it back in. If you have an application that is connecting to a remote database server, and that database server is down, right? There's no possible way that you can write software to troubleshoot that issue, right? So some errors are completely unhandled. You can't handle them at all. But some errors can be unexpected, or some errors can be anticipated and protected against, right? You can anticipate that bad things will happen, right? And then handle those errors, right? That's what we mean by error handling. You detect them, right? Some errors are simply fatal, right? That you should let your program die. You want to let the program die at that point because it is unrecoverable, right? And that's what we've kind of been doing up to this point. Anytime somebody gives us bad input, if we're expecting 3 command line arguments and the user only gives us 2 command line arguments, there's no way that we can compute the result that they want. So we echo an error message and we end the program prematurely. Now we're going to change that strategy. Since we're now writing libraries, we're going to use defensive programming instead. That's fine to do that in the main, but now that we're writing our own functions, if you're inside a function, you want to detect those errors and then handle them appropriately. And the defensive programming is simply going to be a look before you leap strategy, right? So if you're at the precipice, you're at on the edge of some ledge, you look before you take another step, right? And if you see that you're on the edge, and if you did take that step, you would fall off the edge and plummet, right? Then you don't do it. Instead, you turn around and you do something else. But after looking, if you say, "Oh yeah, I still have some steps here to go. I'm perfectly fine," then go ahead and take that step, right? You look before you leap. Now we saw this mistake in a lot of exams where you were expecting 3 command line arguments. So how do you check for that? Well, if the number of command lines arguments is not equal to 4, then we echo an error message and quit. We saw it reversed, right? Where people would just simply grab the values from argv1, argv2, argv3, and then afterwards check for it, right? That's not looking before you leap. That's leaping before you look, right? You think, oh, I could just go ahead and jump off the edge of this cliff, right? And oh, oops, I made a mistake as you're falling all the way down, right? Don't do that. Look before you do your error checking, the very first thing in any function, right? i.e., error checking is the first thing you do in any function, right? Don't do anything else until you're assured that any operation that you do execute within that function is safe to do so. And to do that, you just use an if statement, right? You check for error conditions before you execute some potentially dangerous code. And if such an error would occur, you don't do it, right? For example, what if I were about to say double x is equal to a divided by b, right? Suppose that those are all doubles right there, right? What's one potential bad thing that could happen there? Yeah, if b is 0, right? Here you would check before if b is 0 before proceeding, right? It's very simple. It's just an if statement, right? But now other programming languages, other modern programming languages use exception handling, which is a completely different approach where you can go ahead and try it. In fact, that's what the key word that they use. Try and jump off that cliff. And if you happen to fall, we'll catch you. And there's that key word, catch. You try something, you catch the error, and then you handle the error. C is not one of those languages, right? C, it does have kind of exceptions, traps and things like that, but it's not something that we're going to use in this course, right? That's much lower level. Yeah, well, you don't do that, right? Well, I mean, in a programming language that has exceptions like Java, yes. You jump because there's a net there that will catch you if you fall, and then put you back up on the ledge and then tell you something happened, you need to decide what to do now, right? But that's not how it works in C. In C, you have to look before you leap, defensive programming, right? What we don't do. In fact, I'm going to put that 3 stars around that. There we go. What we don't do, right? We don't print an error message, right? We don't exit the program, right? Again, that's not very flexible. We're now writing our own library functions. If we want our library functions to be flexible and usable, we don't take the decision-making process away from the person that's using our library. Imagine if the math library did this, and you called square root on a -1, and it quit every time you did that, right? That's not a very usable library. Then that puts the onus on you to do error checking instead of it setting it like not a number and then letting you decide how to handle that. It doesn't print anything because, again, the vast majority of software is not written for humans. The consumers have that perception that all the software is for them because all they see as software is their phones, their desktop computers, whatever other consumer devices are out there. That's the tip of the iceberg. The big giant iceberg sitting under is all automation, right? That's the whole purpose of software. And there's nobody sitting there staring at the screen looking at your error messages or looking at your standard output. Instead, you use a proper logging system. So those two things are not how you handle your errors, right? You don't do the dangerous operation. Instead, you return. In fact, I'll put it as a keyword here. Return from the function with an error code, an integer, that indicates the type of error. Right? By convention, 0 is going to be no error, because this is consistent with everything else in C. Was there an error? False. No, there was not an error. 0. Was there an error? True. 1. There was an error of type 1. True. There was an error of type 2. True. There was an error of type 3. Right? Otherwise, so non-zero values indicate some type of error. Okay. Now, I want to take a little bit of a digression before we go back here and look and see how we would do it. I want to show you how POSIX does it. POSIX stands for Portable Operating System Interchange. Right? Don't ask me where the IX comes from. Right? POSIX compliant systems have some basic error codes. Right? In fact, let me go ahead and give myself some more room here so that this always comes up. There we go. All right. POSIX, unfortunately, it only defines 3 error codes, right? And again, an error code is an integer, an error of type 1, an error of type 2, an error of type 3. So the POSIX standard, which is, again, the Portable Operating System Interchange X, whatever X stands for, right? Exchange, interchange, whatever. One of them is EDOM. E stands for error, and DOM stands for domain. It indicates an error in the domain, the input of a function call. Typically, these are used for the math library. So, for example, square root of -1. Now, remember back to your algebra days or whatever. I don't know where they introduced functions, first of all, but they have 2 terms. A domain of things that you map from, and a range of where things map to. And so likewise, we have an E-range error, right? Indicates an error in the range, the output of a function. For example, log 0. What's the value of log 0? Undefined, but if you put on your calc hat for a moment and you take the limit as it approaches 0, it's going to go down to -infinity, right? Square root of -1 is not a number. You gave me bad input. E-range means I'm going to give you bad output because you gave me something that is kind of defined but not really defined, and so here's inf, or -inf. The third one that's used is I've never actually seen it, and I've never actually been able to forcibly cause it, but an illegal byte sequence, right? I don't even know how to, right? Each one of these is defined in a file called errorno.h, a header file, the error number library. Error no stands for number. I think it's kind of British way of doing it, right? Number 1 Downing Street or whatever. Their abbreviations are NO for number rather than NUM for num, right? In the event of one of these errors, a global variable error no is set and to one of those 3 possible values. So let's go. I've got a demonstration set up over here. Let's see, where is it? General. There we go. Error demo, right? That shows how these things work. So for example, if I call square root on the value b here, 2, right? There's no error there at all, right? It's going to output a result, whatever the square root of 2 is, 1.41, blah, 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 right? And then it's going to output the error number, right? And there's no error here, so what would you expect it to output here? 0. By convention, no error, right? What if I called square root on -1? That's going to be an EDOM error, all right? And so we'll output an EDOM error here. Now, these are macros, and I'll show you how they're defined here in a second. But you can check for them. After executing this potentially dangerous operation here, did it result in an EDOM error? If so, then you can output this message here. Did it result in an E-range error, an illegal byte sequence error, etc., or was there some other type of error, right? Error messages can be accessed with this other function over here. We haven't gotten to strings here, but it'll output a human-readable message version of this, right? Then I'm showing you the third way of doing this, or the third option, the third type of error here. That if I call log of 0, I'm going to get an E-range error, right? And these are all mysterious numbers. Do we predict what kind of numbers are going to be output here? Obviously, the first one is going to be 0 because there was no error. But what number corresponds to an EDOM error? Right. 1, maybe? Does it matter? Right. I've gotten rid of those magic numbers here, right? Instead of having to remember if it was 1, 2, 3, or some other random number, right? I am using almost human-readable words here, EDOM. I can read that and understand what it is. Now, granted, they probably should have been a little bit more verbose here, and I would have done like error domain, right? Or domain error or something like that. But they wanted to be short and sweet about it, right? Let's go ahead and run this. General. GCC, error demo, right? And let's go ahead and take, oops, I also need to link in the math library. And let's go ahead and take a look at the output of this. There we go. So in the very first result here, it was 1.41 or 1.4142, that's the square root of 2, and there was no error here. By convention, it's 0. Right? The other one was the square root of -1, right? It looks like an EDOM error on this system ends up being value 33, right? That's just because that's what they put in their header file. It was an EDOM error, right? The human readable message here is numerical argument out of domain, right? So it's not all that helpful. The other result of log of 0 is going to be -inf, right? And that error was 34. Why? Probably because it was listed right after the other one, right? There's no special value to 33 or 34. They're just different types that have different names, right? And the message here was that there was a numerical range out of scope, or numerical result. The output was out of range. Okay. You can actually look these up. In fact, we could maybe I can link to it directly in here. Yeah, I can. Neat. So. Let's jump. Oh, no, it's not. Okay, fine. We can search for it, though. Error H. Source code. Nope, nope. Where are you? Maybe this one. Come on. Yeah, there we go. Oh, nope, that's exactly the same one. I want the full. This looks like it should be good. It's got all of them. No? Come on. I swear I had a link to this earlier. Error no source code. Fine. Source code. Maybe this one. That might be the one I just went to, though. Come on. We'll open up a bunch of these. Nope. Nope. There we go. Finally, a full-fledged POSIX compliant error codes, right? So there are lots of errors here, right? Resource deadlock would occur, right? File name too long, right? I wonder where those EDOM and ERange fall. EDOM. Oops, where is it? No? Find ERange. This does not look like a POSIX compliant system then, right? Oh well. I swear I had one. Maybe that's not it. That's not it. Come on. Nope. 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 Okay. I'm not going to waste any more time here. But you kind of saw with that one example that it probably listed all of these things out, and there were dozens and dozens and dozens of different errors. The POSIX compliant system only says that it has to support at least these three. But of course, it can define other errors that you would actually use if you did any sort of embedded systems programming, right? Or any sort of systems programming. What I want to do now, though, is I want to take a cue from them. I want to do what they've done, but for our application. Okay. Let me go ahead and close this out, and let's go back over to our financial application here, where we're doing a loan application, and we computed the monthly interest, round of cents. Right, and we put all the documentation over here, okay? Now, let's rethink this compute monthly interest payment here, okay? Now, first of all, in the demo that we did on Tuesday, we did, I think, circle statistics, and we freed up the return value here by using two pass-by-reference variables. I want to do the same thing here so that I can use this return value here as an error code. To do that, what do I need to do? Instead of returning the monthly payment, I'm going to put that into a variable at the end here, double monthly payment. Right? And I'm going to return that using this variable right here. Now, is that the correct way of doing it? Nope. What did we do? We passed not a regular old double variable. What did we pass? A pointer variable. Right? That means that we no longer have to return the value over here. What we can do is, initially, we can go ahead and make this a void function. Ultimately, what I'm going to do is make this an int function that returns an error code. Okay? Now, before we get into the actual code down here that we need to implement in order to support this, what's the very first thing that we should be doing? Yep. Look before you leap. Error checking is the very first thing you do in any function. Okay? So, what kind of errors should we anticipate here? What kind of bad input would be bad input for a principal, bad input for a rate, bad input for years, and even a bad input for a pointer variable? Let's start with principal. Negatives? Okay. If principal is less than, what about 0? Does it make sense to take out a loan for $0? Probably not. So I'll go ahead and say that anything that's not positive. Now, what should I return here? Should I return 0, first of all? No. Why? Because that indicates no error. We've already identified this as an error condition. So you ain't running out of any numbers here anytime soon. If you can't do 0, what's next? 1? Okay. Or you could go back to the error no source code and just start grabbing random numbers, right? All right, so else if. What's the second error condition here? What about the rate? Well, remember oh, did we not put it in the... okay, we didn't put it in the documentation here, but usually the rate is between 0 and 1, right? So if the rate is less than 0, right, or the rate is greater than 1.0, then that's an error condition. Now, you can, of course, get into quibbling and say, well, it's a 0% rate. Well, there are loans. There are free loans out there, right? Really, really low interest loans out there that could be 0. You could also quibble and say, well, nobody has a 100% loan rate. except for loan sharks, right? Which is illegal. There must be some threshold here based on legality, et cetera, et cetera. I don't want to get into financial legal laws here, right? We'll just go ahead and keep it simple like this for now. Should I return 1 here as well? I could, but why not? I want to be able to distinguish between these 2 different types of errors. You gave me bad input for the first parameter, or you gave me bad input for the second parameter, or you gave me bad input for the third parameter. Right? So, ain't running out of any numbers, so just keep going up. 2, say. Right? Else, if. What's a bad value for years? Years. Negative, certainly. 0, here's your loan. Now you have to pay it immediately back. Right? Here's your money. Now give it back immediately back to me. Probably not. You have at least 1 year to pay it off or something, right? And I'll return 3 because of the same pattern here. Else if. What about monthly payment? That's a value that I'm actually going to set. So I don't need to look at the input value that's stored at that location. But what is potential problem here when I go to access that value and put something into it? If it's not pointing to anything valid, right? How do I know? Now, I can't say, all right, what is all the memory that belongs to this program? All right, that's the operating system's job. But there is at least one thing that I can check. For null, right? Exactly. So if the monthly payment is null, that is definitely an error because you cannot dereference a null pointer or Bret Hart will come and smack you upside the head, right? So return. Again, I'm not running out of numbers, so 4. Okay. Now we can actually get into the computation here. First of all, can I declare another local variable called monthly payment? Nope. So what I'm going to do is I'm going to rename this result. I round the result to the nearest cents, right? And then I can't return the result anymore because that's my error code. What do I do instead? Monthly payment is equal to result. You could, of course, do monthly payment up here and set it equal to this, and then do that, and then round it, etc. You don't have to have this other variable here. I don't like that pattern because when I'm messing around with pointers, I only don't want to do it once, right? And I only want to do it at the end of the function. Is that the end of the function, though? If we got to this point, line 21, everything's okay. How do I tell the calling function that everything's okay? Return 0, no error. Was there an error? False. No, there was not. Excellent. Now that I've changed this, I need to, of course, change my signature over here. I need to change my prototype. And I should probably also codify that, right? For any errors, this function returns a non-zero error code. Now, if you wanted to document all different 4 types of errors, that's fine. Go ahead and do that. We don't have time to just write that out, but it would be a good idea. Computes the monthly interest for loan payment or payment for a loan, original principal, blah blah blah. Certain number. The result is placed in the pass by reference variable, monthly payment. Right. So I'm telling you how you're getting your result. You have to give me a bucket to put it in, just like scanf. You have to give it a bucket to put that in when it reads it from the standard input. Right. Nice. Right. Except that when we go to use this, and I want to compute the monthly interest rate, say int monthly payment, and I'll go ahead and call this function now. So I also want an error code. Int error code is equal to a call to this function. The examples that we were doing, I think, was $10,000. The rate was 5%, 0.05, and the years was 5 years, kind of a car loan there. So is that how I pass that on to that function? This is a regular old variable, right? Does it expect a regular old variable? As the 4th one right there? Nope. So how do I take that regular old variable and change it into a pointer so that I can pass it off to the function? Ampersand, just like scanf, right? Excellent. Right? Now I could printf the result is equal to %f, all right, $sign, and I'll print all that. I'll print out all the decimals to show you that it's successfully rounding as well, with error code equal to %d and the line, and monthly payment and error code. There we go. And then of course I need to include it. I need to include my financial.h. There we go. And I need to compile everything. So quick review here. How do I compile just the financial.c file? What flag do I need to use to compile? -c, financial.c. Right. Oops. Now that I'm using null, what do I need? I need to include the standard library .h. There we go. There. That produces financial.o. Right? And now I can go ahead and compile demo.c and financial.o together to produce an executable file here. Of course, I need to link in the math library. Oops, what was wrong? %f, %d, monthly payment, error code. Say again? Oh, thank you. Duh. There we go. When I run this, of course, I will get $188.71, which, according to my memory, that was the value, right? Hopefully, right? And there was no error. There was no error there. What if we gave it a negative principal? What error would we expect there again? 1, was it? Okay, error code of 1. The result was 0 because we'd ended up not changing the monthly payment. But the result is kind of irrelevant because we know that an error occurred here. Right? What if I did, say, 105% interest loan? That's an error code of 2. Right? All right, testing these all out. 0 years. Pay it back immediately. Right? Error code of 3. How do I force it to test the last one here? I pass it null. Stupid idea, but that's how I'm testing my, oops. I need to change this back to 5 years. There we go. Stupid idea to explicitly pass null, but some functions actually have you do that, and it changes the behavior. We'll look at a couple of examples later on. And an error code of 4. Okay. Excellent. So undo, undo, undo. There we go. I'm convinced it works now, right? And because we just wrote it, we remembered all those numbers. Come back three months from now. Are you going to remember what error code 1 was? What error code 4 was? How many error codes there were? Right? Nope. Just like I had to try to look it up, the error no here, the source code, right? I have no idea that e name too long 36, right? File name is too long. That corresponded to 36, right? I want to take a cue from the POSIX system here and use human readable error code messages for these things. One way of doing that is like they've done and define. Not here. Let's go over here. I could define what? Negative principal error. And I'll define that to be 1 so that I don't have to use this mysterious magic number here. And I can use that English readable term instead. That's one way of doing it. I'm going to show you a second way of doing it. Let's see. Using a new concept, enumerated types. Okay. An enumeration is just an ordered list of things. Right? That's what it means in English. If I enumerate something, I list them out. Here's the first thing. Here's the second thing. Here's the third thing. Right? For example, days of the week. Right? Months of the year. Or, in our case, error codes. Right? Generally, you want your list to be fixed, and like days of the week. They ain't making any more. Right? There are 7. They're not taking any away yet. Right? Et cetera, et cetera. So that is a perfect use case to define an enumerated type where you can use English words to describe your list. Right? To do that, here's the syntax. I'm going to go into code mode here first. Right? Type def enum with opening curly brackets and then closing curly brackets. That's short for type def definition. I'm going to define my own type, and it is all one word. Enum is short for an enumeration. Within the curly brackets here, I am going to provide my list. So let's do one for the days of the week, first of all. What's the first day of the week? Sunday, okay. Any other votes? No? Some people do it on, start their days on Mondays? No? Okay. I agree, Sunday. Sunday is the first day. Comma. What's the second day? There's no controversy there, right? Monday. Tuesday. Wednesday. Thursday. Thursday. As I'm typing these out, what are the days named for? Does anybody know? Most of them, yeah. Saturday. There we go. So Sunday, of course, that's just the sun, right? Monday is the moon. Tuesday is Tyr's Day, right? Wednesday is Odin's Day, right? Thursday, Thor. Friday, Freya. And Saturday is the exception there. That is going to be, that's one of the Titans, right? The Saturn, right? Right? It's one of the Titans, not Zeus. It's one of the proto-gods or whatever, right? So there we've got our little etymology lesson here today. You could do the same thing with months, right? What are those named for? This month is September. Okay, that makes sense. But things like July. July was named for Julius Caesar. They added a month, right? And August. Augustus Caesar, right? So they added another month because they needed, it didn't always used to be 12 months, right? That's just our calendar right now. At the very end here, what we do is we give this type a name, day of week, right? Followed by a semicolon. So note here in your list, everything was delimited with a comma, but at the end of the list, it's a declaration, just like a prototype or a variable declaration. We're declaring that there's this new type of variable called day of week. Some observations here. Right? You use type def enum at the top. Right? Inside curly brackets, you provide a list. Now, syntactically, you could put them all in one line, but that's not very readable. So stylistically, you should do one to a line, right? Delimited by a comma. Delimited by a comma. There we go. At the end, you provide a name of the type. The name of a type of integer is int, lowercase. The name of a type of double is double, right? This is a brand new type, right? Now that's a user-defined type. We can declare, now that this is declared, we can declare variables of that type. Oops, I'm in code mode here. Sorry about that. There we go. Right. At the end, you provide a name. Usually, you use upper camel casing. Right. That's the modern convention. There are other conventions that you can use. I'm not going to go ahead. I'm not going to use them. But you're free to use them as long as you are being consistent about it, right? Actual values, use an upper underscore casing. Right, there we go. Or sometimes this is referred to as snake casing. It's never looked like a snake to me. Like camel casing, that makes sense because of a hump of a camel. A snake crawling on the ground, maybe? I don't know. I don't know why people call it that, but I always use upper underscore casing because that's what it is, right? You're uppercased, if you're using underscore, that's the casing there, right? Pitfall. Right? Internally, this is nothing more than syntactic sugar. Syntactic sugar. There we go. So syntactic sugar is just syntax that makes the language richer, more flavorful, right? More flexible. Internally, it's being represented by integers. Internally, each value is represented using an integer starting with 0. Right? So for example, Sunday, the example that we just did, Sunday is the first day, has a value of 0 because it came first. Monday has a value of 1, right? ... What about Saturday? Has a value of 6. Why? Because we started at 0, and there are 7 days in the week, right? So this leads to bad things if you abuse it, right? So let's take a look at the usage, right? This is proper usage. Proper usage. You can go ahead and create a variable called day of week, or of type day of week, today, right? And you can even set it equal to one of those values, right? For example, today is Thursday. So I can set it equal to Thursday. I can create another variable here, day of week, tomorrow. And I can set that equal to Friday. I can reset them. I can do whatever I want with them. I can even check for them, right? If day is equal to, I don't know, Saturday, then printf Mavs kick off preseason play. I don't have tickets. Your tickets are free. I encourage you to go, right? Nobody follows hockey. Hockey? Yay? All right. They did very well last year. Come on. Support them. Anyway, improper usage. I'd totally be there if I got free tickets. Today is equal to today plus 10. That's legal. Why? Because they're just integers, right? You could go today, which is Thursday. What value does Thursday have, by the way? 0, 1, 2, 3, 4, right? 4. 4 plus 10 is 14. It does not wrap around to the beginning of the week, right? Do you see a value in here that would take on the value 14? Nope. So it would end up being an illegal value, an invalid value, but it's perfectly fine to do this. Not even your wall flag will catch something like this and say, you can't do that, you shouldn't do that. Right? It's just syntactic sugar that the compiler takes care of assigning all these values for you. Right? It's really no better than using the defines. Okay? So don't do that. Don't do this. Right? Instead, use the proper usage of you want a variable of that type, you set it to a valid value, you'll check it for valid values. You don't set it to anything else. Okay? So now let's go ahead and demo this. Using this with error codes. ... Okay? Come over here. Now where you typically define an enumerated type is in a header file for the functions that use it. And it typically goes up at the top. So I'm going to do that here. I want to define a type for error codes, an enumerated type. What was the syntax for that again? Type, def, enum, opening curly bracket, closing curly bracket. Let's give it a name before we start. Well, what is it? Error type? Right? That's fine. If you wanted to, you could, of course, prepend this with financial error type, right? So that you're not conflicting with any other libraries that may define an error type somewhere. Okay, I'll just keep it simple now for now. What types of errors do we have? Oh, good. Save that idea for later. Right. What was the first type of error again that I've erased now? Negative principal error. Okay, come over here. Negative principal error, comma. What was the second type of error? Invalid rate error. Years, invalid years rate, years error. And what's the other one? Null pointer error. Right? Again, I'm using the convention here that I am going all upper casing, underscore casing on these things. But now, as you predicted, that there's a problem here. If I just leave it like this, what values correspond to each one of these? The first one is 0, 1, 2, 3. Is 0 by convention an error? Nope. So to solve that problem, what should we do? Put in a dummy value here, no error. Right? There we go, with a comma. By the way, there is an Oxford comma here. You can the last comma is optional. You can put it in there if you want to. Leave it off if you want to. Just be consistent about it. Okay. Everything is indented. Everything has one value per line, right? And they're all delimited by commas here. Now that I have this type, I don't have to rely on an integer anymore. I can say, no, it returns an error type. And over here in financial, I can go ahead and use those values. Right? Not that my memory is any better for any of this stuff, but there we go. At least it's readable now, right? Invalid rate error, invalid year error, and now I do remember that one. Null pointer error. Right? And what do I do for no error? No error. It is case sensitive, so you have to spell them correctly. Let's try compiling this again. GCC-C to compile a library, financial.c. There we go. Now over here, you'll note that if I compile this, it's not going to complain about it. Let's find out. GCC financial.o, financial, or not financial, demo.c. Right. Oh, and then of course, bring in the math library. There we go. Right. It's not going to complain that I'm treating my error code not as an error type, but as an integer, because why? The compiler sees those as exactly the same. This is for humans, right? This is not for compilers. This is for humans to read these things and say, okay, I understand what you're doing here. That in the event of no error, you do this, it's all good, you can print it out. In the event of an invalid year error, well, now you need to go back and fix something with a year or something. Right? This is all for human consumption. Right? The compiler doesn't care about it. You can do it, error type. Right? It'll still treat it like an integer so that you can print it out as an integer. Now, how do you achieve something like we saw with the error demo, where we were able to print out the actual human readable error message? That's going to require strings, and we're not there yet. Okay? All right. So there's our demo using error codes. Oh, wow. We've got plenty of time. Any questions so far? Because at the end of this, I wanted to show you one more demonstration. It's a tooling demonstration. Oh, yeah, go ahead.
If you wanted to like increment an enum into, or an enumerated type into like a different one, so like with today, if you wanted to increment it after a loop, is that something that's like you do? Or?
You could do something like this. Today, maybe okay, right? Today plus plus, right? That goes from Thursday to Friday. That's fine. But if you started at, maybe not, if you started at today is equal to Saturday, and then you did today plus plus, right? This is invalid. Why? Because what comes after Saturday? Oh, well, Sunday comes after. No, now it's 7, right? But what you could do is very okay. You could say that today is equal to today plus 1, and then mod out by the number of days that there are. What am I doing there? Today is Saturday, right? Saturday plus 1 is going to be 7. Mod 7, what's the remainder of 7 divided by 7? 0, which takes us back to Sunday. So doing a trick like that works, right? And in fact, what there's another trick that tricks are for kids, so don't do this in general. But another trick that I see often is number of values. That you would put this dummy thing at the end, right? Number of values. What value does that now receive? 0, 1, 2, 3, 4, 5, 6, 7. It tells you the number of valid values up there. And now what you can do is you can use this in your code somewhat, not very easily, because it always ends up being number of values plus 1, or minus 1, sorry. Or no, number of values, right? There, yeah, that'll work. Right? That's in my opinion, that's a hack. Don't do that. But it is something I've seen common enough that I mention it. Right? I'm going to erase it from the notes so that you don't get the idea that, oh yeah, this is a cool hack, I want to do this. Right? If it works, fine. And if it confuses the hell out of you, then ignore what I just said and don't use it. Okay? But that is very okay if you know, again, nobody's making any more days of the week, right? Nobody's making new months, and they haven't since Augustus apparently, right? So until we go on the monthly metric system of some sort, arguably there should be 13 months, but nope, not yet. All right. We're having a hard time getting Congress to even eliminate daylight savings time, right? The House passed it, but the Senate has not. So, and daylight savings time is what, a month away? So it'll be another year at least, unfortunately. All right. So tool demo. There's this tool called valgrind, and I want to show you what it's good for. Okay. I'm going to close all of these and open up a different valgrind demo here. Right. So ignore all this stuff for now. Right. And let me go into general. Right. GCC valgrind demo.c. There we go. Ignore that. Ignore. Right. There. What I did there is the opposite of the wall flag. It suppressed all warnings because I don't want any spoilers here about something bad that's going to happen. Okay? Now let me go ahead and run this program. In fact, I'll give myself some more room here. Right. A.out. Right. Oops. Nope. Dang it. That's not what I wanted. Uncomment this. There we go. There we go. GCC. Again. Oh, it looks nice and clean because there are no warnings here at all. Right? So when I go to run it, I get a segmentation fault. The problem with that is, where the hell did it happen? Does it tell me what line number it happened on? Nope. Now, I do have some print statements here that might give me a hint. Right? It printed 4 things. So I must have gotten past this. I must have gotten past this. And so maybe it's somewhere in here. Right? And this is a simple enough example that the answer is yes, that there's something wrong with these 2 print statements right here. Right? Let's go ahead and take a close look at it and see what's wrong. So A and X are an integer and a double, 42, 2.5. Then I create 2 pointer variables and successfully point them to the appropriate types. Right? A is stored at pointer memory address whatever and holds a value of 42. That works. X is stored at memory address, holds a value of 2.5. And then I reset those. Does this look right to you? What am I doing? I forgot. Correct. If I wanted to set the values, I forgot to star it. So what did I end up doing instead? I set the memory address. I set the pointer to point to memory location 42. I set the other pointer to point to memory location 2, right? In other words, do those memory locations belong to me? Nope. They might not even exist. In any case, it detects that I am illegally accessing those pieces of memory, and it's on what line? On this line and this line right here. And it ends up with a segmentation fault. Now, if I had a much more complicated program, thousands of lines of code in hundreds of different files, dozens of different files, right? Locking that down is going to be very, very, very difficult, especially if you are relying on print statements. Print, right? Then you have to trace the entire code to find out what line of code was it on in which file, right? I'm going to show you a tool, a preview tool. We'll look at this tool several times throughout the semester that will help you to lock down those kind of errors. To do that, what we need to do is we need to compile with a new flag, G. Right, I'll explain what the G does here in a moment. Valgrind demo. Come on. There we go. I'm still using the W flag here because I don't want to. I'll show you. If you use the W flag, then you're done. There's no demonstration here at all because it tells you. Oops. There's no demonstration here at all because it tells you strongly what you're doing wrong. Right? Warning, 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 warning. The problem with the wall flag is that it's a static analysis tool. Right? So GCC's wall flag is a static analysis tool. It examines your code before it is compiled for potential issues. If a seg fault occurs during the run that the linter, that the static analysis tool, the wall flag, was not able to detect, how can we tell what line or lines the error occurred on? For that, you need a dynamic analysis tool. Right? A tool that examines a running program after it has been compiled. So static, dynamic. Static is pre-compiled. In this context, static means pre-compiling. Dynamic means while it's running. Right? Code is static. It just exists. It's there, pre-compiling. Dynamic is when it's actually running. Right? It's actually doing something. Right? So let's come back over here and show you how to set this up. First of all, again, I'm going to suppress the warnings because I don't want. Now you have spoilers here for what's wrong. But you use the G flag. Okay? The G flag is for debugging purposes. You can compile with the G flag in order to preserve metadata about the code. In particular, variable names, function names, and line numbers, most importantly. If you don't compile with the G flag, the compiler doesn't care that you had 50 lines of code or 30 lines of code or whatever. It took your lines of code and translated it to assembly, which is a completely different language. There's not a one-to-one correspondence to this chunk of assembly is actually what line 3 was. And then the next 3 chunks was what line 4 was, right? It's going to optimize it and change it so dramatically that the original lines, they're gone. Right? But if you tell it, preserve those lines because I want to debug this and I want to analyze this, then we'll have those line numbers and we can actually view it. Right? I'll show you both ways here in a second. But now let's go ahead and run this program. Again, it's going to result in a segmentation fault. I'm going to run this through the tool called valgrind. Don't ask me what the name is for. You probably look it up on the Wikipedia page. Valgrind a.out. Right? So instead of running the program directly, I'm going to run valgrind, and I'm going to tell valgrind, run my program, simulate my program, and tell me what's going on while it's running. And a large report will end up coming out of it. It's obviously going to be slower because you are using one program to simulate another program. And it comes back with this full report. There's the output that we expect. But then an error occurred. An invalid read of size 4. Remind me, what's of size 4? 4 bytes in this case. What kind of variable has 4 bytes? An integer. Right? So there's a hint right there that I'm trying to access an invalid integer. Where? At line 21. Now that I've preserved the line numbers, I can jump to line 21 here and see what I'm doing. Okay, well, the only type thing I see here is a pointer to the A. Okay, well, that just prints the memory address. That should be fine. And then I see that, oh, I'm dereferencing that pointer. I wonder if Bret Hart is going to, sneak up behind me. Am I dereferencing a valid pointer or not? I see, oh, okay, I set it equal to 42 here, right? Which is, oops, no, come on, terminal, there we go. Which is actually what it's telling me it is right here. That's hexadecimal, 2A. What is that in regular decimal? Hex to decimal. Online, calculator, whatever. Hexadecimal to decimal. Convert. What memory address is that? 42, right? Exactly what I set it to up here, okay? If you make changes, okay, well, I shouldn't have done that, so I'll go ahead and get rid of that. You need to recompile with the G flag, right? Don't worry about the rest of this. We will talk about the heaps and memory leaks later on. Leak summary here. There's one error from one context, no leaks, we're good to go, right? So let's go ahead and now recompile it with the G flag. Actually, let's compile it without the G flag. And I'll show you the consequences of not using the G flag. So if we run it, of course, I'm going to get, nope. I need to do that and then recompile it and then run it. Right? I get a segmentation fault. Now it's time to fire up valgrind. Valgrind, tell me what's wrong. Remember, I did not use the G flag, right? And so this report, however, is telling me that it happened somewhere in main. I don't know where, because you didn't tell me to preserve the line numbers. So I don't know what line number it was, right? You didn't use the G flag. It's some mysterious value here, right? One block leak summary. Where's the actual error? There it is, right? Invalid read of size 4, address 00. I wonder what that is. What did I set that address to? Null, which is 0, right? That's what it's using as its placeholder for null. So that tells me that there is a null pointer error here on some line, but I don't know what the line number was because I didn't preserve them. So let's go back up, preserve the line number, and rerun valgrind so that it can tell me, indeed, what line number did it happen on? 27. Right? There. Found it. I was dereferencing a null pointer. Sorry, Bret Hart. Get rid of that. There we go. Here's another example. I don't know if this will end up being a GCC. Nope. This ends up being just garbage value, right? So what am I doing here? I am making an integer pointer point to a double, and I am making a double pointer point to an integer. No segmentation fault here at all. But I am getting weird values. Those shouldn't be 0 and 0. They should be 42 and 2.5, right? But they end up being 0, 0. Let's find out if valgrind can detect that I was doing something wrong. I'm not sure that it will. Nope. Unfortunately, we've reached the limits of this tool. You'd probably have to come up with a different tool, and there are plenty of other tools. If you're interested, go ahead and go to the course GitHub repo. In some other tools. This goes way beyond, I'm just telling you that there's this document out here. This goes way beyond the course. Where is it? Tips for troubleshooting. Here we go. Troubleshooting tips. There we go. So, the first thing you do when you're troubleshooting bad code is to test, right? That's what you're doing right now. Make sure that you have a plenty of test cases and that they're all passing and that they're all good to go, right? Then the second thing you do is make sure that you're using the wall flag, the linter flag, right? Then you can use a static analyzer. If you want to, of course, you can use Clang, and what it'll do, it's kind of like another wall flag, but it's Clang is a different is not GCC. It's a different compiler. You can actually tell it fully analyze my code and tell me anything wrong with it. I wonder. Let's find it. Let's test it. Clang. I call it Clang, but it's short for C language, I think, right? And fully analyze. That was it, right? Analyze my valgrind demo here. And you get a report that comes back that looks something like this. I think that it produces a bunch of files here, and then to actually view it, how do you view it? Darn it. Nope, apparently it didn't come up with anything. All right, but you can also use it as a static analyzer tool. Scan build gcc foo.c. So let's try that. Scan build. Oh, scan build. Scan hyphen build. gcc valgrind demo.c. Oh, it's not installed on VS Code. Darn it. I'll ask and see if I can install that. Unfortunately, that's not going to be an option then. And I'm pretty sure that that infer is not installed. Which infer? Nope. Unfortunately, infer is another static analysis tool that's free. I think it's from Facebook. And it can be used to analyze code as well. You can download and install these things in your own machine if you want and test them out and play with them. But if you want to go way beyond what this course covers, then there's a couple of tools here that I've just curated over the years. All right. Valgrind. Very easy tool to use. All you need to do is use the -g flag. If you encounter an error, just simply run valgrind on your executable. And it comes out with a report. Sometimes most of the times it's useful. Some of the times it won't find what the error is. If we had fully automatable tools, guess what? We wouldn't have to write any code at all. All right, any questions? No? Somebody asked online, where can I get these notes? You can get them on the GitHub page here. My GitHub page, there's the URL. Go ahead and zoom in there. And then, of course, all the notes are here. This is fall 2022, and we are all in 194. Right. So there's all the notes, all nicely marked up, too. Right. Exactly as I've been presenting them over here. Right. Although I'm in dark mode. I don't know if you like dark mode or not, but dark mode versus light mode here, whichever is easier on your eyes. All right, I'll see you in your hack session today.